So this is from our example. This is from our example 9.1 here. Okay. So this has a Laplace transform that is 1 over s plus a with region of convergence greater than minus a. So similarly for the second term, if you know that the Laplace transform is s plus 2 with region of convergence that is greater than minus 2, then you know that this should correspond to a time domain signal that is e to the minus 2t u of t. Okay? So hence, if you combine these two, right, x of t should be equal to this e to the minus t minus e to the minus 2t times u of t. Now, if you have different regions, if you're looking at this Laplace transform with a different region of convergence, then it will correspond to a different time domain signal. Okay? So if you look at a Laplace transform with this algebraic expression here, then other than this region of convergence, there are two other possibilities. Right? One is the strip between minus 1 and minus 2, and one is to the left of minus 2. And each one of that corresponds to a different time domain signal. Okay? So we can look at another example. Right? So suppose that now you're looking at a left half plane to the left of minus 2. Okay? So suppose that you're looking at a region of convergence that is to the left of minus 2. So if the region of convergence is to the left of minus 2, then for each one of these transforms to exist, their corresponding region of convergence must be this part and this part. Okay? So for this to hold, this means that when you split into two terms, this first term must have a region of convergence that is less than minus 1, and this part should have a region of convergence that is less than minus 2. Okay? And this corresponds to minus e to the minus t u of minus t and minus e to the minus 2t u of minus t. This corresponds to 1 over s plus 2, the real part of s less than minus 2. Okay? And these identities we get from example 9.2. Right. So if you substitute this back into the above, you find that x of t is actually minus e to the minus t minus e to the minus 2t u of minus t. Okay? All right. Now you can do the same for this example here. Now if the region of convergence of x is between minus 2 and minus 1, right? If this should be between minus 2 and minus 1, then you should have region of convergence corresponding to this in the first term and corresponding to this in the second term. Okay? So in this case, 1 over s plus 1 minus 1 over s plus 2. The first term should have ROC corresponding to the real part of s less than minus 1. And the second term should have ROC corresponding to real part of s greater than minus 2. Okay? All right. So for this term, the inverse transform is this. And for this term, the inverse transform is what we get on the previous slide. All right? So then x of t is this minus e to the minus t u of minus t minus e to the minus 2t u of t. Okay. These are just examples of how we can identify the time domain signal by looking at the patterns of the Laplace transform that we have. Okay. Now we got these results simply based on what we learned from examples 9.1 and 9.2. But by introducing more general properties, right, things like linearity, differentiation, convolution, things like that, we will then be capable of observing the patterns of more complex cases. Okay, and that's what we want to talk about next. Okay, but all of these procedures, you will see, are very similar to what we had for Fourier transform. Okay. All right. So let's start from linearity. Okay. So here we introduce several properties of this Laplace transform that will help us identify, the time domain signals. Okay. So linearity is pretty straightforward. We already had this for many previous cases as well, right? Discrete time transform, continuous time transform, Fourier series, all of them satisfy linearity property. So suppose that x1 has Laplace transform capital X1, x2 has Laplace transform capital X2, then a linear combination of x1 and x2 will have a Laplace transform that is the linear combination of capital X1 and capital X2. Okay. So the only thing that that you need to really be careful with is how to specify the region of convergence after performing this combining. Okay. So in order for this Laplace transform to hold, right, this means that x1 must transform to capital X1, right, meaning that the s here should fall within R1, and that x2 should be able to transform to capital X2, which means that the s here should belong to R2. So for both of these to hold, the region of convergence, the values of s, should belong to both R1 and R2. Okay? So after this linear combining, the region of convergence must contain the intersection of R1 and R2. Okay? But the thing here is that it can actually be larger. Okay? In certain cases, it can potentially be larger. Now, whether or not it can be larger really depends case by case on the problem you have. But in general, it should always contain the intersection of R1 and R2. Right? And this is simply based on the fact that both of these transforms should hold. Okay? All right, now let's look at an example. So suppose that x of t is x1 minus x2. where we know that x1 has Laplace transform 1 over s plus 1 with region of convergence greater than -1. So it's this region here, right? This is R1. And x2 has a transform, capital X2, that is 1 over s plus 1, s plus 2, with region of convergence also greater than -1, okay? So for this case, we have two poles at -1 and -2, and the region of convergence is this part, right? This is R2, okay? So by observing this, you'll find that if I take a linear combination of x1 and x2, which is what we get here, then the Laplace transform, right, of x of t should be the linear combination of the Laplace transform of x1 and the Laplace transform of x2. And the region of convergence should at least be the intersection of these two, which is, the same, okay? Right. So by the above property, we know that x of s is 1 over s plus 1 minus 1 over s plus 1 times s plus 2. Okay? And the region of convergence should contain, right? So in this case, R should contain the real part of S greater than -1. Okay. But the question is, can it be larger? Okay, can it be larger? Okay. So we can just put this together. This will give us S plus 1, S plus 2. And in the denominator, we get s plus 1. Okay? And you see that s plus 1 cancels out. So what we get is just 1 over s plus 2. All right? So if you look at this, this is a rational transform with a pole at a single point -2. So the region of convergence can be either the right half plane to the right of -2 or the left half plane to the left of -2. But since we need to contain this intersection here, therefore, it can only be to the right of -2. Okay? So this has ROC, that is the real part of S greater than -2. Okay? And that this indeed contains the real part of S greater than -1. Okay? Okay. Let's continue to look at other properties. So almost all of these properties we've looked at before. Okay. So the next one is time shifting. So suppose you have a transform. Suppose x of p has a transform that is capital X of s with region of convergence R. Okay. So then if you have a time shift of the time domain signal, right? If you have a time shift of a time domain signal, then you can show that the Laplace transform would be e to the minus st naught times this x of s here. Okay. Now for this transform to hold, basically this x of s must exist. And for x of s to exist, s must belong to the region of convergence R. So the region of convergence for this case is still R, right? The ROC does not change due to time shifting. Okay. All right. Now, what if you're looking at shifting in the S domain? So suppose that you look at this shifting by S naught in the S domain. Then this corresponds to e to the power S naught t times x of t in the time domain. Okay? Now, for this transform to hold, right? For this transform to hold, we must be looking at values of S such that this thing exists. Okay. Now, this thing exists if S minus S naught belongs to R. So this means that this exists if S belongs to R plus S naught. Okay? And really, for S naught, only the real part affects the convergence. So we can write it as R plus the real part of S naught. All right? Okay. All right, so again, to show why the region of convergence should be this, right? Notice that for this Laplace transform to hold, you need to be looking at a value of S such that this transform exists. And this means that, we know that this transform exists if S minus S naught belongs to R. Okay? So if you say that S minus S naught belongs to R, then this means that S should belong to R plus S naught, which is this. Okay? So you can write it as R plus S naught or R plus the real part of S naught. It doesn't really matter. Okay? All right. So if you look at it on the S plane, then originally, if this is the region of convergence R, then this S domain shift will shift it by the real part of S naught. All right. Now, if your S naught just so happens to be a pure imaginary value, then there is no shift, right? There's no shift. The ROC is still the same. Okay. All right. Now, the next is time scaling. Okay. So if you scale the time axis by a factor a, then you get the Laplace transform 1 over the absolute value of a times x of s over a. Okay? So all these derivations are the same as in the case of the Fourier transform. So the only thing you need to be aware of is the change in the ROC. Okay? So for this transform to exist, it means that x of s over a must exist. Okay? Now this exists if S over A belongs to the region of convergence R. Okay? So this transform exists if S over A belongs to R. So this means that S must belong to A times R. Okay? So the region of convergence R1 is the original region of convergence scaled by A. Okay? So suppose that this is the original region of convergence, and if you assume that A is, between 0 and 1, if you assume that A is between 0 and 1, then your new region of convergence will be shrinked to AR2 to AR1. Okay? Now it's possible for A to be a negative value. Okay? It's possible for A to be a negative value. So if A is negative, then you actually have sort of a reversal of these 2 points, right? So this AR1 becomes, negative, and AR2 becomes positive. Okay? So for A less than 0, you have this reversal of the boundary points. Okay. So a special case is when you choose A to be -1. Right? So if you choose A to be a -1, then you have x of minus t, which is a time reversal. So you flip the time domain signal around, right, about the origin. So if you look at the time reversal of x of t, then the ROC will also be reversed, right? So originally, if the ROC is r, then the ROC of the time reverse signal is minus r, okay? And this is a consequence of this. Okay. Any questions up to this point? Okay. So let's continue. So what we have next is conjugation. Okay. So if you have, this, if this Laplace transform holds, then you can show that the complex conjugate of the time domain signal has a Laplace transform that is the complex conjugate of the Laplace transform of x, okay, at the point S complex conjugate. Okay? And this is, quite straightforward to show, right? Because if you have, right, if you're looking at the Laplace transform of this x star of t, then this is x star of t times e to the minus st dt, right? Now suppose you bring out the complex conjugate so that you have the integral of x of t e to the minus s complex conjugate t and a complex conjugate outside. Okay? So you can bring this complex conjugate outside of the bracket, right? You have a complex conjugate here. So then this complex conjugate goes away, but you need to add a complex conjugate to S. Okay? So if you look at this thing inside the bracket, this is the Laplace transform of x at the point S star. And the whole thing is the complex conjugate. Okay? So this gives you x of S star, the whole thing, complex conjugate. Okay? So, it's a sort of one-line derivation of this. Okay. So, right, for this to hold, you simply, need this S star to fall within the region of convergence of R, okay? But the region of convergence does not depend on the imaginary part. So if S star falls within the region of convergence, S must also fall in the region of convergence. So the region of convergence does not change in this case, okay? Still remains the same. Okay. Now, if you look at the special case where x of t is real, so if x of t is real, this means that x of t is equal to x complex conjugate of t. So if x of t is real, these two are equal in the time domain, which means that in the S domain, these two also should be the same. Okay? So then, if x of t is real, and if we know that x of s has a pole or 0 at s equal to s naught, okay, then x of s must also have a pole or 0 at the complex conjugate of s naught, which is s naught star. Okay? So what this is saying is that if A is a zero or pole, so what this is saying is that if A is a zero or pole of x of s, okay, then I think this can be more simply said. Okay. So I think this can be more simply said. So basically this holds since x of s naught complex conjugate is equal to x star s naught, which is x of s naught complex conjugate. Okay. So this is saying that if s naught is a zero, then x of s naught is 0, okay? And the complex conjugate of 0 is still 0. So if s naught is a 0 of x, then it means that s naught complex conjugate is also a 0 of x. Okay? Now, if s naught is a pole, then this means that this is infinity, okay? And the complex conjugate of infinity is still infinity. So if s naught is a pole, then s naught star is also a pole, okay? So this is 0 or infinity, all right, depending on whether s naught is a 0 or a pole, okay? So if s naught is a 0, s naught complex conjugate is also a 0. And if s naught is a pole, s naught complex conjugate is also a pole. So if x of t is real, the zeros and poles must always come in pairs. Okay? It must always come in pairs. It cannot come alone. Okay? So we can see an example in 9.4. All right, we didn't really mention it then, but if you look back, this is indeed the case. Okay? So if you look back at this example here, x of t is real, right? X of t is real. Now, you see that you have 2 zeros at these 2 points, and these 2 zeros are complex conjugates of each other. And you also, you have 3 poles, right? One at -2, and 2 other at -1 plus minus 3j. So you see here that for any complex pole, its complex conjugate must also be a pole, okay? So if you look at it on the S-plane, this means that if you have a 0 here, you must have a symmetric 0 here. And if you have a pole here, you must have a symmetric pole here. Okay?